Hello everybody and welcome back. This is the third in a three-part video series walking you through making your own demo boards for the 18F4550 and programming the 18F4550. In our first demo board we got a LED blinking. Then in our second demo board we added both digital and analog input, and now in our third demo board we're going to add USB communication with a desktop or portable computer. Please visit my website www.18f4550.com or my YouTube channel 18F4550 videos. This video is going to be a quick summary since I'm going to be moving soon. Later on, I'll shoot a full-length documentary series for this USB demo board. But for now, let's do a quick crash course in getting our USB communication going. Okay, so if we go to www.18f4550.com, here's my page. It's kind of minimalist at the moment. I definitely plan on updating it as time goes on, but I'll try and keep the links to the demo boards at least relatively similar to what they are now. So if we go to demo boards, USB demo board, then we'll see this page for the 18F4550 USB demo board. Once I'm done shooting this video, I'm going to add a YouTube link to it here, but other than that, the page will pretty much stay the same at least for a while. So here we have a parts list and a circuit diagram, and then we have a firmware and host software download, and then some pictures of the breadboard version and the perf board version. So the first thing we're going to do is we're going to download the 18F4550 USB demo board firmware and host software to our desktop. So we'll choose Save As. Before we get to unzipping our host software and firmware download, let's take a quick look at our circuit diagram. I'll quickly highlight the differences between our circuit here versus the I/O demo board in our previous project. Some of the additions are, here we have a 20 MHz external oscillator crystal, and the internal circuitry of the 18F4550, how we're going to configure it, will up this 20 MHz to an internal working frequency of 48 MHz, which is necessary for high-speed USB communication. We have one additional smoothing cap here that's required by the USB circuitry. We have some additional LEDs and resistors, a PPTC, a self-resetting fuse to protect both our circuit and our desktop computer in case there's a short in our board at some point. Of course, we have the USB connector, that's definitely new. And then on the right side of the diagram here, I've drawn these USB connector end views, which will be helpful when you're wiring your circuit up. Let's take a quick look at our parts list also. Mostly the parts list is the same as the I/O demo board. Here at the bottom is where most of the differences are. X1 is the 20 MHz oscillator crystal, and of course we have our USB connector, and then our self-resetting fuse, our PPTC, and then I recommend Jamco for those three items, and then as long as you're ordering from Jamco, they have very good prices on USB cables. You also want to pick one of those up. So here we are back on our desktop. So here we have our 18F4550 USB demo board downloaded zip file, and we're going to choose extract all, and of course I already extracted it before I started the video to save time. So here's what we'll get when we're done extracting, is we'll get this folder here, 18F4550 USB demo board. So if we go into that, in that folder we're going to find all the microchip MP lab files. So this will be our firmware. This is what we will load with either the PIC-Kit 2 or the PIC-Kit 3 into the 18F4550. Then if we go into this directory here with the same name, 18F4550 USB demo board, that will take us to our host software files. I wrote these in Microsoft Visual Studio 2008, but I didn't use any especially new or fancy features, so it should import into Microsoft Visual Studio 2010 Express Edition without a problem if that's what you're using. If you don't have any Microsoft Visual Studio version on your computer now, you can go to Microsoft's website and download the Express Edition of Visual Studio 2010 free. So, returning back to the directory we were in a moment ago, the original directory from the download, we're going to take a look at the firmware first, and then we'll take a look at the host software. But before we get into the firmware, let's consider a little bit of background on that. We'll find if we do an internet search on microchip USB stack or USB firmware stack, that will take us almost immediately to this page on the Microchip website that they have devoted to USB communication. Now, chips other than the 18F4550 can perform USB communication, including chips in the PIC24 and 32 line. And Microchip has this USB stack that they've developed, which works with all these different chips, and then they have various examples for different types of USB communication and some different host software examples also. So here are some of the features of the microchip USB firmware stack. By design, it's compiler independent and chip independent, and also USB communication type independent. And also it supports double buffering, also known as ping pong buffering. These four things might sound like a great idea, and if you plan on using different compilers and chips and you need bulk data transfers for USB and the absolute fastest possible transfers and so on, they are great ideas. But the problem is it makes the microchip USB firmware stack version of USB firmware 14 files and more than 5,000 lines. And not only the number of files and the lines, but additionally the code is very difficult to read. There's many conditional compilation statements, and if it's difficult to read, that means it's going to be difficult to modify for your own use. So what I did is, taking the microchip firmware stack as a working example to begin with, I essentially kind of did a streamlined version of that that's compiler specific, which is specific to the microchip C18 compiler, and chip specific to the 18F4550, of course, and is specific to a type of USB communication known as HID, Human Device Interface, which is not especially good for bulk data transfers, but is the simplest, quickest, easiest way to do USB communication. Also, I eliminated the double buffering, which allows for only half the data transfer in a given amount of time, but makes the code much more simple. And the result is 3 files plus a linker file, which is a total of 4 files. So the firmware is 3 files and only about 1,200 lines, plus the host software is about 500 lines. So the firmware and host software together is still a little bit under 2,000 lines. Quite a bit, but manageable. Okay, so now let's get back to taking a quick tour of our firmware. So when we open up our firmware project file, we're going to find that we have, in addition to the linker file, we have 3 files, main.c, usbstuff.c, and usbstuff.h. The linker file I left completely unchanged from the version of the linker file for the 18F4550 that's in the microchip USB firmware stack. Some of these particular settings here are specific to the USB memory locations and the interrupt structure of the 18F4550. So we definitely want to include this in our project. Then MPLAB will use this linker file rather than the default linker file with the MPLAB install. If you don't include this linker file in your project and you allow MPLAB to use its default linker file, then USB communication will not work. So this is definitely essential. So now let's take a look at main.c. So we have some includes and the chip config section. Mostly the chip config section is similar to the previous demo boards. Most of these features here, we just turn them off. The big difference is that the FOSC setting now uses the external clock rather than the internal clock. And then the first 3 settings are particular to setting the timing for using the external clock, taking that in as 20 megahertz and turning it into the working 48 megahertz within the 18F4550 that we need to perform USB communication. Then scrolling down, we have global variables, function prototypes, some interrupt routines which are not used at the moment. Everything's done in polling. And then we get to main. So in main we have USB init is called first, and that's in usbstuff.c. Then we have main init that's in main.c, just down here. And then we enter our infinite while loop, where we alternately call USB tasks and main tasks over and over. So let's take a quick look at the function that's called first here, USB init. That's in usbstuff.c. And here we are in usbstuff.c. We have some includes, global variables, our USB device descriptors. Those are part of the USB spec. And eventually we'll get down to USB init. So here what we're doing is setting our special function registers for USB communication and initializing some of our global variables. And then at that point, USB init is done, so then we're going to run main init. Main init is really just pretty much standard initialization statements of some basic registers, the same as we saw in the first 2 demo boards. Then we're going to go into USB tasks, which is in usbstuff.c. And we're going to have to scroll back down a bit. And here we are in USB tasks. So USB tasks essentially steps through each of the states that the USB communication standard defines as we go from detached to attached, powered, and so on. Eventually, checking the special function registers for errors and things as we go. Eventually, we will get to this function call here, which, when all the functions below execute, will lead to our configured state, at which point we're ready to begin data transfer back and forth. So here's some of the functions that perform the setup. And then eventually, when we get down to two of the functions at the end, and here they are, we're going to have transfer from host to device via endpoint 1 and transfer from device to host via endpoint 1. These are the two functions that actually provide the information as far as updating the LEDs on the board and reporting the state of the switches on the board to the host. So once we've run USB tasks at least once or multiple times until we've gotten to the configured state, then when we run main tasks in main.c down here, first we check and make sure we're not in one of the states that isn't yet configured. And then once we're in the configured state, and again, once I've moved and I have a chance to neaten up the documentation and everything, things like this commented out block of code I'll definitely eliminate. But there's still some odd comments and stuff, and a lot of comments missing at the moment. Continuing down, we'll get to the code that actually transfers our data. So first we check a special function register here to make sure that there aren't any more transactions pending. Then we have our code that receives the buffer from the host and updates the LEDs on our circuit board appropriately. Then again, we're going to check and make sure that all our pending transactions are complete. Then we're going to have our code that's going to check what the state of the 3 switches on the circuit board is and then set that into the buffer that the host can read. So that concludes a quick overview of main.c and usbstuff.c. usbstuff.h is mostly defines type defs and structs that are defined by the USB spec that we have to implement. And then we have more defines down here, more structures to allow our USB communication, more defines, and eventually we'll get to our function prototypes at the end. That concludes a quick tour of our firmware. Now let's take a look at our USB host software. So if we go into the directory with the same name as the download directory, then we can open that in Visual Studio. And the first thing we'll see when it loads is our form. We only have one form for this application. So we have our info label at the top, and then we'll report our switch states here, and then with this radio button we'll choose our state for LED 3. And then with this drop-down box we can use LEDs 4 through 11 to display a number in binary on those LEDs with a value of 0 to 255. So if we take a quick look at the code, we have some defined statements, some global variables, and then we have some additional namespaces we have to bring in. And then we have 7 functions here, and these are taken directly out of the microchip USB firmware stack examples that are Windows API functions that will allow us to perform USB communication. Then we have our constructor with some quick initializations. Then we have the large block of code. Here's some global variables. Then we have the large block of code designed by the Windows Form Designer. Let's fast forward through that. Then we have essentially our events down here, form 1 load, clicking on the info label, attempting a connection, and this is the USB connect function, which is mostly taken out of the microchip USB firmware stack examples. This is where we'll call those 7 Windows API functions to set up our USB communication. Then down at the bottom here, we're going to have the events to handle our radio buttons being chosen, and then that checkbox and drop-down box. And then also our code to update our switch states. That concludes our tour of the host software. So our final step is going to be to get a current compile for the host software and the firmware. So if we rebuild our host software, and for some reason something wrong with my Visual Studio install, I often get that linker file error first, and then if I recompile, it compiles clean. And there we are. Rebuild succeeded. So now we can exit Visual Studio. And if we go back to our firmware directory, and choose our compile button, and there we go, build succeeded. And of course we want to save our workspace. So now we have a currently compiled hex file in our firmware directory, and then if we go to the directory with the same name and then debug, that's where we'll have our host software executable. Now that we have our firmware hex file and our host software executable file, we're ready to load our firmware into the 18F4550 and then try out the desktop executable. So here we are in front of our computer with our completed demo board circuit and our trusty PIC-Kit 2. First thing we're going to do is connect the PIC-Kit 2 to our 6-pin programming header as before. Now we're going to open our PIC-Kit 2 standalone programming software. And sure enough, the PIC-Kit 2 auto-detected that we're connected to a circuit with an 18F4550 in it. So we'll go to File, Import Hex, and then we're going to navigate to our desktop. And 18F4550 USB demo board version 1.0. And one more folder, and sure enough, there we have our 18F4550 USB demo board version 1.0 hex file. Double click on that, successfully imported, and we're going to write. And programming is successful. So now what we're going to do is close out of the PIC-Kit 2 software. And zoom in on our demo board. I'm going to turn my speakers up just a bit. Remove the PIC-Kit 2. And then we're going to plug the A end of our USB cable into our USB connector. And since our circuit board is a true USB device, we should get the doink sound from the operating system. And sure enough, there it is. So the way our board is set up here, LEDs 0, 1, and 2 indicate the states that we saw earlier in main.c, stepping through all the way to configured. And this LED at the bottom of the board here, 12, that's just a power LED. Anytime the computer is powering the board, that LED will be on. Now, notice that we disconnected the PIC-Kit 2 first and then connected our USB cable. We always want to do it in that order. This circuit really isn't set up to handle multiple power supplies. Therefore, it's really better not to leave the PIC-Kit 2 connected at the same time as the USB connector, since that also provides power. So now what we're going to do is we're going to pan back and we're going to start our application. Try and get the circuit board in view of the screen at the same time. There we go. So if we navigate to I've shrunk the window down so it's visible on screen here. If we navigate back down to that debug directory and the USB demo board desktop software executable, here's what we'll find opens. Check that's visible on camera. And we see the connection is successful in our status label here, and that currently none of the switches are pressed and the LED 3 state is chosen to be off. So if we, with these radio buttons here, if we turn LED 3 on or off, we can switch it back and forth. And if we press any of the 3 buttons for switch state, the display on our application will update. Pressed or not pressed, and in fact we can press 2 of them at once, or even all 3 if we like. And finally, the LEDs 4 through 11 on the front of the board as we're viewing it now could be used for debugging. You could put statements in your firmware to set those LEDs on at certain times to indicate which parts of the code you're getting into or not getting into. Or, as we've configured our desktop software here, we can check this box and then choose a value from this drop down, anywhere from 0 to 255, to display on LEDs 4 through 11 binary. So there's 1, there's 2, there's 3, and so on. So for example, 127 would be all but the last LED on, 255 would be all on. And there we have it. So we've demonstrated both input and output via USB communication between our computer and our circuit board. So everything's a definite thumbs up, working great for us. Congratulations! You now know how to make a demo board and write software to perform USB communication with the 18F4550. So, what's next? I'm going to move to Detroit very soon, Tuesday of next week actually, so some of these projects are going to have to be on hold at least for the moment, but at least so far, here's what I have planned. First, I'm going to do my video on how to set up an ESD workstation in your house or apartment. So if you're not familiar with taking ESD precautions already, then I'll definitely give you an introduction to that so you can handle the 18F4550 with knowing that you won't hurt it. After that, I'm going to do an 18F4550 example using both SPI and I2C communication and also involving an LCD display. And then after that, I'm going to come back to the USB material and I'm going to do a USB motor controller. So rather than simply blinking LEDs to show output, we'll actually have working DC motors and servos and steppers attached to the board. Also, I'm going to eventually add sufficient comments and neaten up the code for the USB demo board project that we've looked at here. These two, I'm not really sure what order I'm going to do them in, but at least more or less this is the roadmap I plan on following. So definitely stay tuned to my website, www.18f4550.com, and my YouTube video channel, 18f4550 videos. See you next time. Welcome back, everybody. Quick update video here. This is the USB demo board section of my website. As soon as I'm done with this video, I'm going to post it right here. And the reason I'm making this video is that here's the previous 2 videos that were already on YouTube. The reason I'm making this video now is that I've done an update to the both the desktop software and the firmware for the USB device example. For the Visual C++ version, I updated it to Visual C++ 2010, and I also went through the code and deleted a lot of the sections where there were commented out blocks of code and so on, and I added a lot of comments in the areas where the commenting really wasn't sufficient before. And also, I added a C# version. That's with C#, Visual C# version 2010. So please check these out if you're interested. They are on my website, and I'll post this video shortly to this page also. And I've got some pretty good project ideas coming up, so please stay tuned to my website and my YouTube channel. See everybody again soon.